Two-dimensional heat transfer. Ain't nobody got time to live in one dimensions. 2D. Now, our temperature is going to be a function of position x and position y. It's a two-dimensional problem. Let's suppose we have a rectangular slab, our favorite material, to evaluate the heat transfer through. The x direction of this slab has dimensions of size A. Along the y-axis, the dimension is B. So you have an A by B rectangular material, and we want to solve the following heat equation. Just like that. So we want to solve the heat equation in 2D. So far, we've only had one term on the right-hand side, partial squared t over partial x squared. But now that we have a two-dimensional geometry, the Laplacian operator, the upside-down triangle squared, now has two components, both along x and along y. Now, we'd like to solve this problem, but first, let's consider the easier test case when the problem is fully at steady state. In other words, the time derivative on the left-hand side is set equal to 0. As you saw previously, this corresponds to the long-time steady-state solution when the transient part of the problem has decayed away. In a little bit, we'll consider the transient part, but let's first just consider the steady-state 2D heat transfer problem where there is no dependence on time. So now the temperature profile is only a function of x and y. Just like that. So we have our governing equation. 0 is equal to the second partial derivative of x and y added together. This is called Laplace's ODE. It's extremely common in science and engineering. There's a technique called the multipole expansion that's used in fluid mechanics, electricity and magnetism, in various fields, physical chemistry. And this Laplace's PDE forms the basis a lot of expansions that we conduct in various physics and chemistry problems. So this is a fundamental problem, not just important for heat transfer, but in all of physics and more broadly in science and engineering. So let's write down our boundary conditions, which we haven't told you yet. So the boundary conditions that we're going to solve for are the following. Let's suppose that in this particular example, the boundary conditions along the x, at both x equal to 0, x equal to a, are fixed at 0 temperatures. So Dirichlet boundary conditions on the left and right. And on the y-axis, at y equal to 0, we have some function of x, f1 of x, which you know. We know this function. It's a boundary condition that you've put as a constraint as an engineer. On the top, there's a different function, f2 of x, that the temperature is fixed at. So it's going to vary as a function of position. It might be some water jacket that you've added around the slab, and that water jacket's going to vary in temperature along the x direction. And therefore, you're going to have some temperature variation along x at y equal to 0, and another separate temperature variation along the x direction set at y equal to b. Again, Dirichlet boundary conditions, but non-homogeneous along the y direction, homogeneous boundary conditions along the x direction. We have our governing equation. Let's write down our boundary conditions cleanly. All right, I've written down the 4 boundary conditions that we need. We need 4 this time because we have 2 derivatives in x and 2 derivatives in y. There's no initial condition because we're solving the steady state problem. There is no initial condition. So we have the left-hand boundary, right-hand boundary, the bottom, and the top. Those are the 4 boundary conditions that we're going to need to uniquely solve this problem. So this is a well-posed problem. Okay. Just because there's an additional coordinate doesn't mean we're going to change our technique fundamentally. The technique that we've learned how to solve these problems for the last couple of weeks is separation of variables. Turns out we can use that technique here as well. Separation of variables works for a variety of different geometries, different transient, steady state problems. So let's just apply the separation of variables technique here as well. Separation of variables, in this particular case, we're going to separate the temperature profile, which depends on both position x and y, into a product of two functions, just like we did before with 1D transient heat transfer, except the key difference is that we're going to take the product of capital X, which is a function along the x direction only, times another separate function, capital Y, which is only a function of the vertical direction and vertical coordinate y. So previously, we did capital X times theta, which was a function of time t. But in this particular case, there is no time. And therefore, we have position x and position y, which are independent variables. So we're taking two functions, each only a function of its own independent variable, position x and position y, taking the product of those two things and declaring that as our overall temperature profile in the steady state case for this problem. So it's still a guess that we can write it and separate the variables, right? That's why it's called separation of variables. And so let's carry on with the technique and see how it differs or see how it's similar from what we've been doing already. So the first step is to make this guess, substitute this formed guess into the original partial differential equation. So if we plug that into our original governing equation, this is what we get. We get this equation right here, just directly substituting temperature T, taking the partial derivatives of x and y of this product. Now, we're going to multiply this through. Of course, this capital X only depends on x, so we'll pass through this y derivative because it's a constant with respect to y, and vice versa for this capital Y function. This is only a function of little y, not of x, so we'll just pass through this x derivative. I'm going to take these two terms, put them on opposite sides of the equation. All right, so we get this separated form where I've taken all the x dependencies, move it over to the left-hand side, all the y dependencies, move it over to the right-hand side. The only algebra step that I did was to divide both sides of the equation from this previous step, divide it by capital X and capital Y, and thereby get 1 over x and 1 over y on each side of the equation. Now you look at this, just like we did with the 1D transient heat transfer problem, you notice that on the left-hand side, this is a function of little x only. And on the right-hand side, this is a function of y only. Once again, you have inequality of a function of x must be equal to a function of y for all x and all y. The only possible way this can ever be true is if they're both equal to a constant and the same constant. Just like that. Now, there is a subtlety on which sign to choose on the right-hand side. We've always been choosing negative lambda squared. You have to start to be a little bit careful when you start doing 2D problems, but we'll get into that subtlety a little bit later. For now, let's carry on with the same procedure. We called it negative lambda squared, we separated the variables, and now you have two ODEs, just like before. Previously, you had an ODE in position x, ODE in time. In this case, we have an ODE in x and an ODE in y. Let's solve those two separate ODEs. So now we have these two separate ODEs to solve. We have an x ODE, which is the same one that you've been solving all along. So you know what the solution is, sines and cosines. And another ODE in y, but there's a small difference, which is that the sign in front of lambda squared is the opposite of what you've been solving along the y direction. So over here, as before, you get sines and cosines because the characteristic equation tells you that the roots of this equation is I times lambda. They're complex, discrete. You get sines and cosines. Just like that. So you get sines and cosines. On the y direction, because the roots of your equations are positive, and it's equal to lambda, so positive roots, plus and minus lambda, you get real, distinct roots, so you get exponentials as your solution. Okay, so we have our y solution, which is going to be constant of integration d, e to the lambda y, plus another constant of integration e, exponential of negative lambda y. You guys are all experts in solving linear, constant coefficient, second-order ODEs. Here are both examples of that. This is why you need to know how to solve ODEs to solve PDEs. Usually when we solve PDEs, it just results to solving ODEs. So if you can't solve ODEs, you can't solve PDEs. That's just the way it works. All right, so we wrote it as an exponential here, but there's another way to write exponentials as linear combinations of the plus and minus roots of the exponential. You guys might have remembered way back long ago, you guys learned about hyperbolic sines and cosine functions, cinches and coches. Do you remember that? Let's write it down. Hyperbolic sines and cosine. Hyperbolic sine of the argument y is the difference of your two exponential solutions divided by 2. The cosh hyperbolic cosine of y is the sum of your two exponential terms divided by 2. Graphically, what they look like is that the sine, hyperbolic sine, crosses the origin at y equal to 0 and then juts off to infinity. Hyperbolic cosine goes to a non-zero value, goes to 1 at the value of y equal to 0, and then juts off to infinity around that point. Okay. I don't know. When I first heard cinches and coches, it seemed like a really weird function to remember. The way I remember it is, gosh darn it, it's such a cinch to remember. So that's how I remember it, and I think now you'll never forget hyperbolic sines and cosines. Gosh darn it, it's such a cinch to remember. So instead of writing exponentials as our solution to the y-ODE, because cinches and coches are just linear combinations of the exponentials, we can instead write our y function as a combination of cinches and coches. Just like that. So now our y-ODE solution looks like some constant of integration alpha, sinh of lambda y, plus another constant beta times cosh lambda y. Why did I call it alpha and beta? I don't know. I ideally wanted to call this C and D because I wanted to, in advance, skip 2 letters and call this some other letter so that I can reserve C and D, so we go A, B, C, D. But then I was too dumb to realize that I didn't skip 2 letters. So if I called this C and D, now D's are the same. So I apparently could do PDE solutions, but I can't count the letters in the alphabet. So that's why I call it alpha and beta. You can call it whatever Greek letter you want. My favorite are xi and zeta. They look very similar to each other. Xi looks like this, and then zeta looks like this. I wouldn't recommend you call it that way because you're going to get confused which one's which. In any case, I've called it alpha and beta. And so at this stage, and the reason why I called it different constants is because I've just taken linear combinations of D's and E's and redefined my constants to alpha and beta, right? That's just to be clear, that's what's happened, right? We can't call it D and D down here because they're not the same functions. Okay, so at this stage, we have our 2 solutions, capital X, capital Y. We can put it into our separation of variables solution and start applying boundary conditions. Because so far, this is just the governing equation. We've made a guess, separation variables, and we're just working on the equations. That's all that we're doing so far. All right, we have the governing equation solutions. Let's write them here cleanly and then start applying boundary conditions and see what happens. So far, we've just solved the governing equation, our x-ODE, our y-ODE that we solved over here. I've combined them using our guess for separation of variables and wrote it as the product. Okay? So the full temperature profile, as of now, is a product of the solutions of 2 separate ODEs, a sine, b sine, lambda x, along the x direction. So we have sines and cosines along the x direction, which happens to be the direction where we have homogeneous 0 boundary conditions, or Dirichlet boundary conditions. And then times a function of y only, which has cinches and coches, which are exponential solutions. Therefore, along the y direction, we have exponential solutions because the roots were real as opposed to being complex. Okay? So it's interesting. We have a product of real roots imaginary, complex roots, real roots. Okay? And that dictates whether we have sines and cosines along the x direction or sines and cosines along the y direction. We'll come back to that a little bit later. But for now, here is a solution to the governing equation, and we have now constants, a bunch of them, alpha, beta, a, b, lambda. Let's start applying boundary conditions here to figure out what some of those constants are. First, the boundary condition 1, which is at the left-hand boundary at x equal to 0, the temperature is fixed at 0. Now we're going to plug in x is equal to 0. So sine of 0, this term dies. We have plus cosine of 0 is 1. So this whole term in brackets first on the left-hand side here is just going to become b. That's the only term left over. And then everything here in the brackets on the right, which are functions of y, are unchanged because we're plugging in x equal to 0 right here, and y is a free variable. And therefore, y is going to stay as is. But that whole thing, so b times this whole thing, has to equal 0 for all y. So the only thing that could make it work is if the constant b were to be equal to 0. Okay? If that train of logic didn't make sense, try it right now. Convince yourself that is the only way you can make it true. It's the same as what we've always been doing. This zero boundary condition will usually get rid of one of your constants of integration, even for the transient 1D heat equation. We've been doing that all along. So same thing here. In this case, boundary condition 1 tells us that b has to be equal to 0. Just like that. Okay? So at this stage, one of our term goes away, just like that. And we keep going. So the equation looks a little simpler. Now we only have sine and then sinh and cos left over. So our second boundary condition at x equal to a. Again, y is a free variable, so that just remains completely unchanged. So the right-hand side stays the same. X is now equal to a. So we have capital A sine lambda times a, which is the dimension of the box. We've been calling it capital L, but now we're calling it a and b. They're just numbers, the dimensions of your slab. We have sine lambda a times all this stuff, which is still a function of y, must be equal to 0. Same train of logic and argument we've been making. So one way to make that true is if a, the constant out in front, were equal to 0. But if you do that, then both a and b are equal to 0, and this whole temperature profile will just give you a 0 solution, the null solution. We don't want that. So to get a non-trivial solution, we have to let sine of lambda a be equal to 0, which gives us the eigenvalues. Again, the same arguments we've been making all along with the 1D heat equation, just along x and along time. So I'm going to skip these steps because they're no different from what we've been saying so far. Just like that. So lambda times a must be equal to pi cycles, n pi, right? Where n are integer values. Therefore, we get our eigenvalues. Lambda sub n is equal to n pi over a. That suggests that there are infinite number of solutions in which this could be a solution to this equation and yet also satisfy this boundary condition. Therefore, it implies superposition of all of these indices n to get the most general solution for the temperature profile. Now, there's going to be an interesting thing happening because this lambda n is going to be n pi over a, which is a dimension along the x direction. That lambda is going to come here inside the sine term. You're already familiar with that. So this is going to become n pi x over a. You've already seen that over and over again. But over here on the y dimensionality, it's going to be lambda, substitute in there, it's going to be n pi y over a. So there's kind of interesting combination, right? Because the variable y is going to go along the vertical direction, but you have the dimensions along the x direction on the denominators. It's going to be n pi y over a for the sinh, and same thing with the cosh, n pi y over a. Let's write down the most general solution, because now we have to sum over all of these with superposition. All right, here's our solution so far using the concept of superposition and linearity of our equation. We have many different possible solutions from the top equation all the way up here based on solving the equation plus satisfying this boundary condition, which means we should add up all of those solutions to get the most general form, and that's where the summation comes up. So we have the summation of only the sign term stayed, and we have two terms that carried through from y. Again, just like the 1D transient heat transfer equation, the coefficients now become a function of, or not a function, but it's going to have many different coefficients, and it's going to vary as a function of the mode number or index n. So alpha becomes alpha sub n, and I've put a little prime above the alpha n and beta n because I've just absorbed this constant out in front a and multiplied through with alpha and beta. So again, we did that with the 1D heat equation as well, right? Same thing, just combining constants because the product of two constants is still a constant. So we just have alpha prime n, beta prime n. Okay, so now we have two constants left, alpha n prime, beta n prime, that we're going to obtain using the other two boundary conditions along the y direction. So let's apply boundary condition number 3. And we'll start to do it a little bit more carefully because now this part is a little bit different from usual. All right, this is boundary condition number 3. We're going to plug in y is equal to 0, leave x alone. So the sine n pi x over a just gets left alone. And here we're going to plug in y is equal to 0. Now, some of you might have been curious, why did I choose cinches and coches earlier? Why couldn't I just left it as exponentials? You could have done that. You could have just kept the y ODE solution, e to the negative lambda y, and then e to the positive lambda y. You could have totally done that. But the reason why we recasted it in terms of cinches and coches is precisely for this reason. It's a convenience reason, purely convenience. Because look what happens. If we plug in y is equal to 0, the sinh function goes to 0 at y equal to 0. Remember, it has a curve that looks like this, goes through the origin, and then goes up. Therefore, sinh at 0 is equal to 0. So this entire term, this alpha prime n sinh term, completely dies at y equal to 0. In contrast, over here, cosh of 0 equals to 1 at y equal to 0. Okay, so it's purely convenience. So now we have only one constant of integration, beta n prime, that gets left over in this boundary condition. If you had used exponentials, you'll get both left over because an x e to the 0 and e to the negative 0 both give you 1. So you get 1 and 1. And so you get alpha and beta both left over. And it's just inconvenient because now you have to use this boundary condition and the fourth boundary condition in parallel. So if you have two equations, two unknowns, it just becomes algebraic a little bit more messy. So purely convenience. You could do that. You're totally fine to do that. Purely convenience. We call it cinches and coches for the convenience here. So what we get when we plug in y equal to 0 here is, like I said, the alpha prime and sinh dies. We get cosh of 0 is 1. So we get beta n prime to be left over. So we get beta n prime. I just move it over into the front. And then we have sine n pi x over a. Again, x is a free variable in this case, so it's just left alone. So we have a summation of 0 to infinity, some coefficient sub n, sine n pi x over a is equal to some function f1 of x. This is just a Fourier series, right? Fourier series for the variable beta n prime. There we have it. So we have one constant of integration, beta n prime, completely determined. So coming back up to our general solution right here, we now know what the betas are. So that's known. And this is just a number, right? A is just a number, f of x, f1 of x, sine n pi x over a dx. This just produces a number. So there are no more unknowns in beta n. It's just a number that we already know. Now, obtaining the alpha n prime, we need to use the other boundary conditions. Let's check that one out. All right, so boundary condition number 4 at the top boundary. Oh my gosh, are you getting tired? I'm getting very tired. Let's just power through this a little bit more, just a little more and we're done. So boundary condition at y equal to b is equal to f2 as some function of x. So I've just here written this right-hand side here, plugged it down here, but let's plug in y is equal to b here. Okay, so now we've plugged in y is equal to b for both of these terms. And now if you think about it, stare at this a little bit and think about it. First, remember that beta prime n is known. Beta prime n, we just figured that out using the top boundary conditions. That is known. It's just a constant, just a number. Okay? Cosh of n pi b over a. Again, for a given n, the index, this is just a number because cosh of some number n that goes 1, 2, 3, 4, it's just an index. Pi is a number. B is just the physical dimension of the problem of your slab. And A is also that. So B over A is just the aspect ratio of your material. Just all numbers. So beta n prime cosh of this whole argument would just be a number given some index n. Over here, sinh n pi b over A is also just a number given the index n. Therefore, this whole thing inside the bracket, this whole dependence with sinh and coshes, would just be some constant that depends on n only. Right? So given an n, the index, this is all just a constant. So let's just call that constant g sub n. Let's just call it g sub n. And then all we need to do is clean this up and rewrite it a little bit. Just like that. So this whole thing in bracket just became some constant g sub n. And all we have is another Fourier series. So we know our constants g sub n. Just like that. So we have g sub n is just equal to this based on orthogonality. So you can see the parallel between beta n prime, which told us about the coshes, right here, using the Fourier series f1. Same thing down here, we have g sub n that tells you something about alpha n and beta n prime. Is just another Fourier series with the integrand f2 as some function of x. Now, are we done? It seems a little weird because we call this whole thing g sub n. We really want to get alpha. What's really going on here? So let's think about this definition for g sub n a little bit, right? I've just written down the definition, how we defined it earlier. This is everything just inside the bracket. So we now know what beta is. We know how to evaluate that because we have an expression for beta n prime. We know what beta n prime is. We also know what gn is. Again, this is just a number. Give me an n, this will produce a number. So this is also known. And what we don't know, what we need for our original equation is alpha n prime. But we can now calculate what the alpha n prime is because we know g of n, we know beta n prime, we know the coshes, this is just a number, this is just a number. Therefore, we can back calculate after we find g and beta what the alpha n primes are. So knowing g is equivalent to knowing what a alpha is. So at this stage, we are actually done. We're completely done. So all we need to do is solve for alpha n prime, and we're all done. Okay, are you tired? I'm pretty tired, but we're all done, thankfully, for this steady state problem. I've boxed 4 boxes, which are the equations that you need to remember. Well, not really remember, but just there's so much gibberish on this board. These are the 4 that represent the solutions. So first, the sum of all of your general solutions up here has the unknowns alpha n prime, beta n prime, which are the coefficients, your Fourier coefficients that you need to obtain for every index n. The beta n prime you obtain by just performing this integral for some function f1. You then obtain g sub n using this integral for f2, which is your top boundary. And then lastly, you solve for alpha n using your now known knowledge of gn and beta n prime. And now you have both alpha prime and beta prime, which go into your overall solution right here. So, wow, that was pretty intense. Beast mode. We just completely beasted this problem at this point. The board is completely full. Now, I want to visualize a solution, but an even cooler visualization is the case where we use the transient solution. So one last comment I wanted to make. I know you're probably tired and probably zoned out and nothing I say will enter at this point, but just consider this at the very end as you think about it after this video is way early on, we did separation of variables. We made a choice about the sign of lambda squared when we had all the x functionality on one side, all the y functionality on one side, and x ODE, y ODE. But then we said, okay, the only way we can make that equal to each other in the very first step of separation of variables is if they're both equal to the same constant, and we let that equal to negative lambda squared. Suppose you said it was going to be positive lambda squared. Then what would have happened is you would have had sines and cosines along the y, and sinh and coshs, or exponentials, along the x. So the roles would have been flipped. Now, trace back to your calculation. If you had made that switch in their roles, it wouldn't work out. And the reason why it wouldn't work out is because, again, of the homogeneous boundary conditions. Remember the transient 1D heat equation that we solved before, we were able to make that solution work when we removed the non-homogeneous boundary condition into the steady state part of the problem, and we had homogeneous boundary conditions to solve the transient heat solution problem, T transient, and that worked out fine. But we had zero boundary conditions to make that work. In this case, just by design of the problem, we had zero boundary conditions along the x and non-zero boundary conditions along the y, which means that we want to get sines and cosines along the homogeneous boundary condition direction. And along the non-homogeneous boundary direction, we use the Fourier series to make those functions work. So if you had gotten sines and cosines along the y direction and exponentials along the x direction, it would not have worked out. So the key point of the Sturm-Liouville theory that we've been talking about is this sines and cosine, which are called eigenfunctions, only work along a direction where we have homogeneous boundary condition. So at this stage then, you might wonder, well, you just specified these boundary conditions to be zero on both ends, but what if the boundary conditions were different? What if this one were equal to some other constant, t1 or t2? Or what if this were even more, equal to a different function f3 of y? Then you no longer have homogeneous boundary conditions along the x as well. Then does this all just break down? Let's consider next what you would do if the boundary conditions along all directions were non-homogeneous. So I erased everything. I was getting nauseous looking at all the equations, so it's good to clean up the board. But my last question that I posed, what happens if the boundary conditions weren't as convenient as I posed it here? What if all four sides were some non-zero number? So just to make things easy, I'm just going to put concrete numbers on all four sides. Suppose that the temperatures on all four sides of your slab was fixed at some given temperature. 3, 5, 6, and 10. Just non-zero numbers in general. Okay, what would you do in this case? Earlier, we had zeros in both sides along x and non-zero along y, but now we have non-zero along all four sides. If you're posed with a boundary condition like this, where none of the sides, or even a partial fraction of the sides are non-zero, you have to divide this problem up into two components. What you want to do is break up the original problem into two different problems. One problem where you have t1 as some function of x and y. That's going to have 0 temperature along the x. So you have homogeneous Dirichlet boundary conditions along the x direction. And you leave the 3 and 6 intact as non-homogeneous boundary conditions along y. You add to that a different solution, t2 as a function of x and y, where now you put 0 boundary conditions along y and leave your non-zero boundary conditions as original along the x direction. And the reason why you want to split it up in this fashion is because now you are guaranteed homogeneous boundary conditions along x or along y. Notice that this problem for t1, we just did that problem. We just did it. The steady state problem where I gave you two zero functions along the x, a non-zero function f1, f2 along the y direction. We just did this problem. So we can fully solve this problem. So we just did that problem. And what we did was we took our full solution t1, split that up using separation of variables into some function of x, some function of y. Just like that, we plugged it in to the steady state heat equation. And then at the point where you separated all the x's, all the y's, it looked something like this. Just like that. And we chose that the constant that each of these has to be equal to is equal to negative lambda squared. And it's good that we chose negative lambda squared, because what this means is that along the x direction, you get sines and cosines. And along the y direction, we got exponentials, or sinches and coches. Exponentials. And remember that when we applied the boundary conditions, now along y equals 0, boundary condition number 3. When we apply that boundary condition, it riddled down to something that looked like the following. The boundary condition at y equal to 0, which in this case is equal to 3, because we're solving this problem right here, it's equal to 3. Because we're plugging in y equal to 0, we got the sinh and coches to work out. One of them canceled, right? The sinh went away, the cosh became 1, so then you end up with some constant that I've called c of n. I think previously we called it alpha n, beta n, whatever. Some constant times sine n pi x over a is equal to 3. And we said, oh, that's just the Fourier series for the c sub n's. And that's why everything worked out. Now, suppose you made the wrong choice. Suppose back here, when we separated the variables very early on, you didn't choose a negative sign here, but instead chose a positive sign. If you chose positive lambda squared, what you would get is the flip. Now along the x direction, you get exponentials. Just like that. And then along the y direction, you would get sines and cosines. Just like that. So the roles are flipped, right? So the x's are written in blue, the y's are written in pink. And therefore the roles are flipped if you choose the wrong sign here. Now suppose we carry it through. Suppose for the sake of argument, you chose incorrectly, but you didn't know. When you get to this step where you invoke boundary condition 3, what you would get is that this would now be exponentials instead of sines and cosines. It would look something like this. Just like that. So if you try to apply your boundary condition, you get c sub n times sinches and coches or exponentials instead, because you're applying y equals 0. What survives are the x's, and so you get exponentials here. Now, this is not a Fourier series because exponentials, or sinches and coches, don't have that convenient property of orthogonality. So up here with sines and cosines, you can multiply both sides by sine m pi x over a, integrate, and then you pop out using orthogonality one term when n and m are the same, and then therefore you get uniquely the coefficient c sub n for every index n. In this case, you can't do that. You can't just multiply both sides by sinh lambda x, integrate from negative a to a, and expect the sinh to be orthogonal. Try it. It's not going to work. Go on Wolfram, integrate a sinh function from negative a to a. You're going to get values that are non-zero for every index n because they're not orthogonal functions. Sines and cosines are special. Exponentials are not special. They're not orthogonal functions. Therefore, this is how it would fail. And this is why you need to be a little bit careful about when you set up your problem, which sign of your coefficients lambda or constants eigenvalue to choose, because otherwise you're going to get into a problem a little bit later. So for this problem down here, for the T2 problem, you actually want to flip it in the other direction because you want sines and cosines along the y direction so that when you apply the boundary condition along the x at 0, x at a, you will get a Fourier series to capture those boundaries. So for this bottom problem for T2, you actually want to set this equal to positive lambda squared so that this problem right here gives you sines and cosines. And the x ODE gives you exponentials, or sinh and cosh. That's how you want to do the problem. As long as you're careful with which direction that you are eigenexpanding, you're eigenexpanding along x, you're eigenexpanding along y, depending on which boundary or which direction you have zero boundary conditions along. You want that direction to have sines and cosines, and therefore you want to come back to here at separation of variables and choose the right sign. Once you do that, this problem is totally solvable. So earlier we did this case very carefully, but you can clearly do it for this case and just flop it, just turn it around from x to y. And the solution procedure, basically identical. Okay? The only difference is that this is a rectangular shape, so you have length a instead of b. So that's about it. Conceptually, no big deal at all. Okay, so now we've fully solved the steady state 2D heat transfer. Let's move on to the transient case, but I would highly recommend that you take a break right now because this problem right now in the transient case, it's going to add another layer on top of the steady state case that we've done here. So I take a quick break, but we're going to now move on to the transient solution to this problem. All right, let's work on the fully transient 2D solution. I've kept the same diagram because a lot of it can be reused. I've made a couple of notable changes. First, the temperature profile they want to solve is now a function of x, y, and time. So 3 independent variables that the temperature depends on. Naturally, because we're solving a transient problem, we're going to have our partial temperature, partial time be resurrected. So now it's a non-zero left-hand side. We're solving the full 2D transient heat equation. I've inserted the time dependence to each of these boundary conditions. I've kept the boundary conditions the same as the previous example, just as demonstration, but they can be arbitrary functions of y or of x, depending on which sides of the boundaries that you're talking about. Still Dirichlet boundary conditions. And I've added an initial condition where at time t equals 0, so at time t equals 0, we have some known function of x and y. So that's the initial temperature profile. We have the slab, it's got some initial temperature profile, and at time t equals 0, boom, we set the walls to be 5, 3, 10, and 6, and we want to look at how the temperature evolves from being an arbitrary function of x and y that we know already to an evolution fixed by these boundary conditions. That's our goal. Now, because we have non-homogeneous boundary conditions for this problem, we do need to break up our problem into a steady state solution, which we already just did. we did the steady state solution, plus a transient. This is identical to the transient 1D heat transfer problem that we already did. We separate it into a steady state solution plus a transient solution whenever we had a non-homogeneous boundary condition. Remember that T1 boundary condition on the left-hand side that we took care of? Same thing here, we're doing it now 2 dimensions. So we're breaking up our total solution, which is the function we want to find ultimately, into 2 parts. One is the steady state solution, T steady state, which is these 2 solutions added together. So this is the steady state solution. So we just did these problems. The steady state solution was this plus this, homogenizing the boundary condition, finding sines and cosines in the right direction, 2 solutions added together. We did in detail the T1 problem, the steady state problem. T2, again, is just sines and cosines along y. The sum of these 2 guys is our total steady state solution. That is what this 2D slab is going towards as time goes out to infinity. The long time steady state solution is what these 2 solutions are. Now, we're going to add to that a transient component that depends on time. Same structure as 1D heat transfer with a non-homogeneous boundary condition. Steady state plus transient. Same thing, now extending it to 2 dimensions. Now, the transient problem is going to be this problem with now homogeneous boundary conditions. Let's draw a picture. It would look something like this. This is the transient problem that we're now trying to find. This is the additional piece that we have to solve in addition to the equations that we've already solved previously for the steady state solution. Now, the boundary conditions are all 0 in this case because we have taken care of all the non-homogeneous boundary conditions for the steady state solution. So all that we're left with are 0 boundary conditions, Dirichlet, along both directions, x and y. And so ultimately, the total solution would be this picture plus this picture plus this picture. So a sum of 3 solutions. Like I said, we already solved T1 and T2 for the steady state. Now we need to solve the transient case. Let's solve this transient case with homogeneous boundary conditions. Okay, let's solve this transient heat equation problem in 2D, because if we've solved this, we solve this whole problem. Now, we're going to do separation of variables like we always have been doing. We're going to now separate x, y, and t. We have 3 independent variables to separate. So I've written the transient solution as a product of a function of x, a function of y, and a function of t. Capital X, capital Y, and theta. As before, we're going to plug this solution into our transient heat equation over here. And if you plug it into your PDE, this is what you're going to get. Before doing that step, I failed to explain one detail about how do you get the equation for the t transient. So the total solution, once again, is the 2 steady state solutions, T1 and T2, plus T transient. Now, plugging this whole equation into the original PDEs, this is the full temperature profile, what you're going to find is first on the left-hand side, partial temperature, partial time, the 2 steady state solutions cancel. They're not a function of time, and therefore when you take the time derivative, these 2 terms cancel. All you're going to be left with is the time derivative of the transient solution on the left-hand side. Now on the right-hand side, you're going to get a sum of 3 terms. Just like that. And therefore, what you're going to get is the Laplacian. Again, the Laplacian in 2D is just partial squared x, partial squared y for T1, T2, which are the steady state solutions, and finally, the transient solution. Now, what we said was we've solved each of the steady problems. And we want to solve the heat equation with 0 boundary conditions. Therefore, what we've already solved are each of these steady state equations equal to 0. Remember, that's the equation we solved. Steady state, left-hand side is 0. 0 is equal to Laplacian of t1. That's the problem we just solved in the steady state case earlier. Therefore, each of these are 0. And therefore, the equation for the transient problem that we're now trying to solve with separation variables is the original heat equation. It's partial t transient, partial time, and the Laplacian of the transient solution in x and y, 2 dimensions. So we recovered the original heat equation. They must be equal with homogeneous boundary conditions. Now, let's plug in this separation of variables for the t transient terms right here and see what happens to x, y, and theta. It'll look like this. So I've skipped one step, but I think you've done enough problems now to kind of be able to see this just in your head. We're going to plug in capital X, capital Y, capital theta into this equation. Again, these two terms are gone. We don't have to worry about these anymore because those are the steady state solutions. They're gone. So we just have, on the left-hand side, we have d theta dt to pop out. That's this term. And then x and y will just pass right through. Over on this term, the Laplacian of t transient, the theta term will just pop right through. And then x and y will each get a partial derivative, which now turns into a normal derivative, because now capital X and capital Y are only functions of x and y respectively. So you get second derivative in x, second derivative in y, first derivative in t, time. Divided through by x, y, theta, all the way across, and you get this equation. It's just an algebra step, but you recover this equation. Now, in the past, when we came to this equation, we made an argument about, oh, everything on the left-hand side is a function of x, everything on the right-hand side is a function of time, therefore they both must be equal to a constant. That constant is going to be equal to negative lambda squared. We're going to make a similar argument, except on the left-hand side, there's a function of x and y. But when you look at this equation, we need to make sure this equality is true for all positions x, y, and time. The only way you can make this ever true under these circumstances, a function of x plus a function of y equals some function of t, is if they're all equal to a constant. Every term. This term is equal to a constant, that term is equal to a constant, that term is also equal to a constant. Let's call them other constants. We're going to call them negative mu squared, negative gamma squared, and lastly on the right-hand side, negative lambda squared as usual, right? Usually we just set this equal to negative lambda squared. That stays the same. But furthermore, we're saying that both the x and y each have to be a constant as well, because there's no other way to combine x's and y such that it's going to be equal to a constant unless they're both equal to a constant. Therefore, the original eigenvalues lambda squared that we had is now just a sum of mu squared and gamma squared. So you can now notice that we're going to have 3 separate ODEs. No big deal. Until now, we've had 2 ODEs to solve at this point. Now we have 3. That's fine. Along the x, we're going to get sines and cosines, right? Because we have the characteristic equation will admit complex roots. So we'll get sines and cosines. Also sines and cosines along y, and then a simple exponential decay along time. Let's write those down. So you get these 3 solutions. Sines and cosines along x with mu, sines and cosines along y with gamma, and finally, an exponential decay. Technically, there's a prefactor constant integration factor of a prime or a1 here, but we're going to multiply x, y, and theta together from separation variables, and that prefactor will just get absorbed into each of the constants of integration for the others, x and y. So let's put all the solutions together at this point. It would look like this long, ugly expression right down here. This is the full transient solution. We have function of time theta, capital X, capital Y. Combination of those 3 terms. That is our transient solution so far. Now, we need to apply boundary conditions. But that's actually not so bad because now we have, again, homogeneous boundary conditions. Here are our boundary conditions. Now, at this stage, you should be able to do a lot of these boundary conditions evaluations in your head. First, let's apply the boundary condition at x equal to 0. That's this left-hand boundary right over here. That's equal to 0. So x equal to 0. When you plug x equal to 0, the sine term right here dies. So this term goes away. Cosine becomes 1. And therefore, what you find is that you just get a. So the entire first term in the bracket just becomes the constant a. That's the only thing that remains at x equal to 0. I hope you see that. Everything over here on the right, because y can vary along the left-hand boundary, there's nothing you can do for this bracketed term on the right. This will just stay as is. But that whole thing, so exponential of negative alpha lambda squared t times a times this function of y must be equal to 0 at the left-hand boundary for all y and time. The only way that we can make that true is if a were equal to 0. Okay, so a is completely gone using boundary condition on the left side. Just like that. So we can make a similar argument for the boundary condition along y equal to 0. At y equal to 0, that corresponds to this one. So along the x-axis at y equal to 0, plug in y equal to 0, the cosine term becomes 1. D sine of 0 becomes 0, so this term dies. And for the same argument we made earlier, the c's have to go away. Therefore, it's a little bit easier now. All we have are the b sine mu x and d sine gamma y. And we have two more boundary conditions. One along x equal to a. So let's do that one. The one on the right. At x equal to a, that's the right-hand boundary, you plug in x equal to a. So we're going to have b sine mu a. This term, sine gamma y, stays as is because we can't say anything about the y. That must equal also 0. Now, one way to make that true is if your b is equal to 0. But if b were 0, you get a trivial solution. Because a is 0, b is 0, you get the trivial solution. You don't want that. So we want the non-trivial solution, which is when sine of mu times a is equal to 0. And those are our eigenvalues. So again, same arguments we've been making all along. So the boundary condition at x equal to a tells us the nature of the mu's. So I've just written that at boundary condition x equal to a, mu times a must be equal to n pi, where n are integer values. Every pi cycle, sine goes to 0. Now, same argument over here for the top boundary condition at y equal to b. So at y equal to b, we have d sine gamma b must be equal to 0. If d were 0, we get a trivial solution. We don't want that, and therefore we get our eigenvalues gamma. Just like that. The only subtlety that you need to remember is that in this particular case, we've chosen a different index m. So n runs over all integers, and it covers this eigenvalue along x. But along y, we need a different index m because for every value of n we have, this can also be freely varied, right? X and y are freely varying. So when you use your boundary condition at y equal to b, this gets pinned at sine gamma b, but along your x direction, this looks like sine of n pi x over a, because we now know what mu is. So this is a function that varies with position x. And for every value of n you supply there, this could take on an infinite number of values in a different index, m. So hand me an n, say if n over here were equal to 1, sine 1 pi over a times x, we're going to have an infinite number of combinations of sine y, right? Sine gamma b to make it equal to 0. Therefore, you need to choose a different index because n and m can independently vary that both satisfy the boundary conditions along the right and along the top. So now you have two indices, n and m, that are both increasing in integer values. All right, let's clean up this solution and write the most general form that we have for right now. So here's our solution so far. All I've done is collect the terms that stayed, b and d, with each of their respective eigenvalues, mu and gamma, plug it into here. So we have sine n pi x over a. We have that multiplied against sine m pi y over b, which came from each of these boundary condition evaluated eigenvalues. And then superposition says I'm going to have many of those terms for arbitrary n and m, and therefore I need a double summation over both indices n and m. Finally, I've taken the constants of integration b and d, combined it into a new constant of integration as the product of those two constants, equal to c sub nm. Now it's two indices because c can take on both fixed value of n and m with degrees of freedom for both to vary. Lastly, I brought the exponential, which is negative alpha lambda squared t. Lambda squared is now known. It's all kind of buried everywhere, but you know that lambda squared is just mu squared plus gamma squared. And therefore, lambda is a function of both n and m, because we know mu and gamma separately as a function of n and m. So we now know what gamma, mu, lambda all are. We just need to obtain the c sub nm. We obtain this using our initial condition all the way back here, right here. Here is our initial condition. Let's use this to obtain our last constant of integration, cnn. So we get something like this. Initial condition, t transient at time t equals 0 is equal to the function as a function of x and y, f. We know what f is on the right-hand side. We plug in t equal to 0, the exponential term goes 1, and we just have this. This is just a 2D Fourier transform, or Fourier series. A equals this, a 2D Fourier series for the coefficients c and m. It's no big deal. You just take orthogonality both along x and y. You multiply both sides by sine n pi x over a, sine m pi x over y. You do the whole orthogonality argument. Boom, out comes this 2D coefficient for c and m. You integrate along y and x, and you uniquely get your coefficient c and m for a given value of n and m. That's it. So here we have it. We have our whole solution. You probably don't know that we're even done because we're so down in the trenches that like, where are we at this point? We're actually done, because we have the full solution here. C sub nm is here. This is just a number, right? We're going to integrate away the y's and x's. It's just going to be a number. We know what lambda is because lambda is just this. It's the sum of mu squared plus gamma squared, as we defined earlier. So we know what lambda is. We can plug it into here. And that's it. We're going to have our full transient solution as a function of x and y. And we can add our steady state solutions that covers the homogeneous, non-homogeneous boundary conditions. And that's it, guys. That's the whole problem. So at the very end, I want to show you, after all this mathematical gibberish, what the solution actually looks like. So let's visualize the solution. Okay. Let's visualize this solution. I've erased everything unnecessary so that now we have the transient solution, the coefficients, and the eigenvalues. Now I'm just going to solve for the transient case. Let's go over to the screen where I've animated this transient heat solution where we have the initial condition of a temperature equal to 100 everywhere. So I'm going to evaluate this first sequence. It is just going to be equal to this. What I'm plotting here along the z coordinate is the temperature right here. And that's going to be a function of both y and x, and the colors indicate the magnitude of the temperature at that particular point. Now, initially, we've set a distribution where the function is equal to 100, a constant temperature 100 all the way across along the domain of 0 to a, which I've set to 1, and 0 to b, which I've also set to 1. So it's a square domain of length 1. Now, what I'm going to do is to quench all signs of that boundary to 0 because we're solving the transient part of the problem where we have homogeneous boundary conditions. So now we're going to evaluate this, and you're going to see the solution decay from the value of 100 everywhere all the way down to 0. That happened a little bit too quickly, so I'm going to play it again. Okay? I coded this up myself, and I feel like I was a student doing a homework problem. So everyone, I've done my homework problem. Let me show you my homework solution. Here it is. I've done my homework. Ah, beautiful. It looks so good. It looks really cool. And I've got to say, every time I show this to my class goes, whoa. So this is the moment, especially after an hour and a half of grungy algebra and calculus. This is a kind of a rewarding thing to see, something beautiful that actually makes intuitive sense. So all this mathematical gibberish that we wrote down and just spent a long time on beast mode just trying to finish this problem, ultimately becomes this beautiful solution that is a Fourier series in 2D. You can even see that early on. You can see the bumps along, right? If you don't blink at the very beginning, you can see the bumps in the Fourier series along 2D. And then that gets quickly dissipated through the exponential that then slowly dampens out to equilibrium. Okay, so this is all I wanted to show you. It's just a really cool application of a transient 2D problem. Of course, what I'm showing you here on the screen is T transient. That is the transient part of the solution. If you wanted to solve this problem I'm showing here on the board on the upper left, where you have non-homogeneous boundary conditions, all you would do is add to the solution I'm showing you on the screen the steady state solutions, which we already solved earlier today. And so the sum of those three solutions, the two steady state solutions, plus the solution I'm showing you here right now on the screen, that is your full solution to the transient 2D heat equation. Oh my gosh, I am tired. My wrist is about to fall off. This is the most rough class in terms of grungy calculus and algebra. From here, it gets easier, and it will become cleaner and cleaner. So if you've watched to the very end, you are pretty amazing, because I can barely watch myself as my wrist falls off writing down all these equations. So congratulations on making it to the end. We'll talk about a different problem next time. See you then.